All right, here in section 7.6, we return to an old familiar topic. It's another section on L'Hopital's rule. So this should be a pretty friendly section. So returning to L'Hopital's rule, let's just remember what L'Hopital's rule said. It said when the limit as x approaches a of f of x over g of x equals the limit as x approaches a f prime of x over g prime of x if the limit as x approaches a of f of x over g of x has the indeterminate form 0 over 0 or infinity over infinity. Remember, the 0 over 0 or infinity over infinity were the only types of indeterminate form where you could apply L'Hopital's rule. And also remember, infinity over infinity is how we generically represent those four different cases. Infinity over infinity, or infinity over negative infinity, or negative infinity over infinity, or negative infinity over negative infinity. So let's do a quick example just reviewing L'Hopital's rule. So here we're going to determine the following limit. The limit as x approaches 0 of e to the 2x minus 1 over x. So write it down because I'm heading off to the chalkboard to quickly do this. All right, hey, here we are returning to an old familiar topic, L'Hopital's rule. And remember, that involves dealing with limits. So in trying to determine this limit, when we try substitution, we see the form we have is the indeterminate form 0 over 0. And when you have the indeterminate form 0 over 0, you can apply L'Hopital's rule. And remember, L'Hopital's rule says the derivative of the numerator, which would be e to the 2x times 2, over the derivative of the denominator. Well, the derivative of the denominator is 1. So now you substitute and you get 2e to the 0. E to the 0 is 1. 2 times 1 is 2. So that was just kind of a quick refresher of L'Hopital's rule. Let's head back to the slides and see where we're heading with this. All right, now remember we saw there were some other off-brand indeterminate forms. When we learned L'Hopital's rule in a prior section, such as infinity minus infinity. Well, there are even more, other off-brand indeterminate forms. Here are a few of them. 1 to the infinity. We don't know what that is. 0 to the 0. That's indeterminate. Infinity to the 0. That too is indeterminate. But just like before, if we have whenever you have an off-brand form, you have to get it into the 0 over 0 or infinity over infinity form before you can use L'Hopital's rule. And there may be some situations where logarithmic differentiation will be a good technique. It will help. So let's look at the following example. The limit as x approaches infinity, 1 plus 1 over x to the x power. That definitely has the indeterminate form of 1 to the infinity. And it should also look familiar to you. In a prior section, I told you exactly what this is equal to. And I also said at that time, later on in the chapter when we would prove it, well, that's what we're going to do right now in this example. So let's head off to the chalkboard and work through this example. And we're also going to see logarithmic differentiation is a good friend of ours. All right, here we're supposed to get the limit as x goes to infinity of 1 plus 1 over x to the x power. And if you try substitution, you'll see this has the form 1 to the infinity, which is an indeterminate form, but we can't apply L'Hopital's rule to it. You can only apply L'Hopital's rule to 0 over 0 and infinity over infinity. All right, so here's what we do here. We look at this limit statement and we say, you know what, let's assume the limit exists and let's just call it y. So we're going to assume the limit exists and we're going to call it y. that gives us y equals, the limit as x goes to infinity, 1 plus 1 over x to the x power. And now I'm going to take the natural log of both sides. And when I take the natural log of both sides of the equation, over here on the right side, since this is something we learned way back when we first started to talk about limits, and we didn't really have to worry about it, so it was discussed way back when we first did limits. Since natural log is a continuous function on its domain, and it's continuous, where x is heading off to infinity, natural log is continuous, you can rewrite this as the limit as x goes to infinity, natural log of 1 plus 1 over x to the x. And one of the nice things about rewriting it that way is, well, there's a law of logarithms. What can I do with this exponent? That's right, I can move the exponent out front. So let me write that down. Natural log y equals the limit as x heads off to infinity, x, natural log 1 plus 1 over x. Okay, now notice what form we have right now. As x goes to infinity, well, this is infinity. It's a bad x. This is 1. The natural log of 1 is 0. So we've turned this form. We've gone from 1 to the infinity to now we're at the form infinity times 0. I still can't take it to the hospital. But when I pull it up here, if I remember an old trick, I can rewrite this multiplication as dividing by the reciprocal. So I can rewrite that as the natural log of 1 plus 1 over x all over 1 over x. Now the form, as x goes to infinity, now the form is 0 over 0. And once we have 0 over 0, we can use L'Hopital's rule. And notice, L'Hopital's rule is only used on the right side of the equation because that's the only side that has the limit statement in it. So let's get the derivative of the numerator. So we have the natural log of 1 plus 1 over x. So that derivative is 1 over 1 plus 1 over x times, now you have to remember the chain rule, you have to do the derivative of 1 plus 1 over x, and that's a negative 1 over x squared, over, okay, the derivative of the denominator, 1 over x. That's not bad, that's negative 1 over x squared. That's kind of cool actually, because now they cancel out. And we have the natural log of y equals the limit as x goes to infinity, 1 over 1 plus 1 over x. Folks, as x goes to infinity, that's going to 0. That's a 1, that's a 1. So you have 1 over 1 plus 0. That's 1 over that, that's 1. And natural log of y equals 1, you can rewrite that as y equals e to the first, or just simply y equals e. And look at how we started this. We started this by saying we're going to assume the limit exists and we're going to call it y. We've just determined y is equal to e. So this is e. So we have just determined that the limit as x goes to infinity of 1 plus 1 over x to the x power is e. And you've already seen that on a prior slide, in a prior section. I told you that's exactly what E was equal to. And I also told you at that time, hey, I can't verify this for you right now, but later on in the chapter we'll be able to do it. Well, we just did it. So let's head back to the slides and see what is next. Okay, folks, that last example really wasn't a surprise because we had seen in an earlier section that was exactly how E is defined. So it wasn't a surprise, but here's what I'd like you to take away from it. Here's what I'd like you to add to the homework. I'm going to give you two more homework problems to practice. Determine the limit as x goes to infinity of 1 plus 2 over x to the x, and the limit as x goes to infinity of 1 plus 3 over x to the x. You're going to do those two, and if you do them correctly, you are going to detect a pattern. You're going to suspect something, and you're going to be able to generalize what you think the limit as x approaches infinity of 1 plus b over x all to the x power is, just by doing those two extra homework problems. Once you detect what the pattern is, once you detect what you think this limit is, so you have an idea what this limit is, you're going to be able to determine a formula for that limit. And that will come in handy as you go forward in calculus. Let's do another one. Let's determine the limit as x approaches 0 from the right side of 0 of x to the x. This is going to be fun. So let's head off to the chalkboard and let's do this one. All right, folks, in this example, we're asked to determine the limit as x approaches 0 from the right side of 0 of x to the x. So straight away we notice the form it has. It has the form 0 to the 0. So you know what? I'm going to ask you to pause the video and you try to determine the limit. It looks very similar. The process is very similar to what we did in the last example. So pause the video, see if you can get the limit. When you're done, restart the video. I'll be here at the board working through it. All right, folks, let's see how you did on this. So I started off by saying, hey, I'm going to assume the limit exists and I'm going to call it y. So I have y equals the limit as x approaches 0 from the right, x to the x. Take the natural log of both sides. And then because natural log is a continuous function, I can pass it through the limit process. And, well, then the nice thing about this is, remember, I can move that x out front. Property of logarithms. They do come in handy. And, well, let's see, look at the form we have now. The form we have now, we started off the form with 0 to the 0. Now the form is 0 times negative infinity. So we've gone from 0 to the 0 to 0 times negative infinity. I still can't take it to the hospital, but I can employ that old trick that multiplying by x, see we have natural log x times x, multiplying by x is the same thing as dividing by the reciprocal. So if I pull this problem up here, I can write it as natural log x over 1 over x. And the form I now have is negative infinity. And as you approach 0 from the right of 1 over x, that's infinity. So I have negative infinity over infinity. That is one of the forms that I said that we generically just call infinity over infinity. So I can now apply L'Hopital's rule. And remember when I apply L'Hopital's rule, it's just to the right side. It's because that's the only side that has a limit statement. Derivative of ln x is 1 over x. The derivative of 1 over x, well, that's negative 1 over x squared. And let's see, the right-hand side, that simplifies to a negative x. Now when we do substitution, we just get 0. So y is equal to e to the 0. Y is equal to 1. And we originally started off by saying, assume this limit exists and call it y. We now know this y is equal to 1. So we have determined that the limit as x approaches 0 from the right side of 0 of x to the x, that limit is 1. All right, folks, let's head back to the slides and see what's next. All right, the end of this section, folks, it discusses growth rates of functions. Knowing how functions grow, it's going to be an important concept in Calculus 2, especially when we're studying infinite series. So when we say growth rates, it's going to be important that you would be able to know that an exponential function grows faster than a polynomial function. A polynomial function grows faster than a logarithmic function. That's what you'll see at the end of this section. I just said that. Theorem at the bottom of page 497, I think it's theorem 7.14. It kind of ranks the growth rates of functions. The text at the bottom of page 497, it also mentions this intuitive understanding for future work on infinite sequences and series. That's something that we're going to do in Calculus 2. So I'd like you to check this out. Check it out, appreciate it. It's going to be something that's going to be kind of important in the future. It can help you have just knowing how things grow. It can just help you with your analysis of infinite series when we get to Calculus 2. But that's it for this section, folks. It's an old topic, one that we're already familiar with. So at this time, you can do the exercises in section 7.6. So go do the exercises in section 7.6, and thanks for watching.